Okay, so we're going to finish up now on section 5.2. So how did the prep part go? Did that go okay? So let's just review what chain rule is so that we can see the parts that we have to have when we go backwards. So remember we have rules we have power rule, exponential rule, log rule, we know multiplication by a constant, addition, subtraction, they all carry through. All of that works like it has been. There's no reverse product rule and there's no reverse quotient rule, but there is a reverse chain rule. So the important part is that we have to have all the parts. So when we look at a function that's a composite function, so one function inside another function, we know that when we do the derivative, we take the derivative of the outside function and we multiply it by the derivative of the inside function. And I've left a gap here because remember, when you take the derivative of the outside function, you leave the inside there. You don't mess with that. So this actually has that inside function still stays in there. Okay, so the important part is derivative of the outside times derivative of the inside. So if we're going backwards, and we see that we have some composite function here, because we can see that composite structure right here, right? We've got a function inside a function. If we want to go backwards, we can't just go backwards unless this piece is here. This piece has to be here. Okay? So this is what we're always checking for. Every time we see a composite function and we want to go backwards and do the antiderivative, the first thing we check is the derivative of the inside sitting right next to it. Front or back, doesn't matter. Okay, so let's look at some examples. So let's start with this one. We're going to start with a couple that kind of progress, so we'll see what you have to have and what you don't. So let's start with this one. So for those of you who are looking at the notes online, this is example 2. Okay, here's our first one. Remember, integral sign says do the antiderivative. dx tells you what variable to do it with respect to. So these two pieces you have to have as part of your instructions. Okay, so I see a composite function. An inside function and an outside function. Inside and outside. So that means the derivative of the inside function, I need to make sure that that's sitting beside it. So I'm going to keep drawing it this way, and I encourage you to do this because it will help you, particularly as we start losing constants. It's going to help you to do it this way. So here's my inside function. The derivative of that is 2x. Is it sitting there? Yes, bingo. That means that I have the complete derivative. It's there in its entirety, nothing extra, nothing missing. So that means I know this part right here is going to get sucked back into the inside, so I don't need to worry about that. All I have to worry about is the outside function. So I know I'll have something to the 6th divided by plus c. What goes in the middle? The same middle. The middle doesn't change. So x squared minus 7. Okay, so what happens if you have this one? So it's a little different. It doesn't have a 2x, it just has an x, and I moved it around to the front. The first thing I see is composite function. I mean, the first question you always ask yourself, anytime you do a derivative or an antiderivative, is it a basic? Is this a basic? No, it's definitely a composite function, so we know we've got chain rule rumbling around. So I need to take the inside and find the derivative, 2x. We already did that. Is the 2x sitting there? No. Do you agree it's sort of yes and no? This part's there. So what do I know about constants? Constants carry through, right? I can be kind of fluid with constants. So what if I did this? What if I rewrote this with a 2x there? Can I multiply by 2 just because I feel like it? Can you multiply a problem by 2? Just no. But if I multiply by 2, what can I do to undo that? What can I multiply by 2? Yeah, divide by 2 or multiply by a half. Do you agree that this problem is exactly the same as that problem? 1/2 times 2 is 1. That's just an interesting way to write the number 1. I haven't changed the problem at all. But now what do I have? Everything I need is sitting right there. So what does this tell me? This tells me that this answer then is that same 1/6, it's the same as that, except multiplied by a half on the front. So I have a 1/2 times the 1/6. And do I need to clean that up? Yes. A half times a 6th, the 12th. Do you have to rewrite it this way? No, you don't have to. In the early going, I recommend that you do, just so that you can keep track of your constants. If you have a different number here, like a 3, I definitely, or a 4/5 or whatever, I recommend kind of pulling out all the constants that are not what you want to the front, making sure you get what you need here, and then your constants will work themselves out. So usually writing down more rather than less is a better plan. So until you get really good at it, I would write down more. So here, I had the full derivative of the inside ready to go. Here, I sort of had it and sort of didn't. The important part is I had the variable, right? Because I can mess around with constants. Can I mess around with variables? Can I just multiply by an x and divide by it? No, no. So that brings us to the third example, which is this one. Is it a basic? No. Composite function? Derivative of the inside? Is it there? Not at all. Not, remember, constants, I can play with constants. Is the variable there? No. So this one you do not know how to do in this class. So this is it's not that it's undoable, it's just you guys don't know how to do it yet. Okay? So this one we're not going to attempt. The important part that I'm trying to point out is you have to have the variable part of the derivative of the inside. Constants? Yeah, we can play with constants. We've been playing with constants all semester, right? We can do that. You can't play with that x. So whatever the derivative of the inside is, the variable part you have to have. Okay? All right, so let's do some more. All right. So let's do this one. No, sorry, E. Okay, so the first thing, what are we supposed to do with this problem? What do these parts tell us?
Antiderivative.
Antiderivative with respect to x. Is it a basic? No. I see a composite. Which one's the inside, which one's the outside?
E to the x is the outside.
This one is the inside, right?
Yeah.
E to the x is kind of this is inside the exponent of the exponential. So this is our inside function. So what is the derivative of our inside function? 8x. Is it there? Well, the important parts, right? I had the x. That's the important part. Okay? So let's rewrite this. Let's go ahead. So if I wanted to, I could then multiply by 8 and 1 over 8. And now do I have everything I need? Does it matter the order of multiplication? No, you can multiply in any order, right? You can add in any order. So this then I can write as 1/8, 8x, e to the 4x squared dx. So now, is this a complete derivative? It is. The entire derivative of the inside is sitting there next to it, which means it's going to get sucked up into it when I do the antiderivative. So now the only thing I need to worry about, outside function. So what's the antiderivative of an exponential?
Same.
The same thing. So e to the same thing, 4x squared. I had that 1/8 out front. Got to include that. Plus c. As you get good at it, you can say, I need an 8. I don't have the 8, so I divide by the 8. You can skip this middle step once you get good at it, but like I said, I recommend that you practice kind of writing it all out first. So does that make sense? All right, let's try this one.
was that not 1? What was that 1/8 like that equal to?
I'm sorry, what?
Why did that equal 1/8 e to the 4x squared plus
Because
c?
there was a 1, so when I finished rewriting it, I had this. Because this is the full derivative of that. So remember, at first I didn't have that. And so there are a couple ways. I needed to have an 8x and I didn't have it. So I made it, but I can't multiply by 8 unless I multiply by 1/8. These two pieces together equal 1, so I haven't changed the problem. So that means this whole part here is the complete derivative, and I still have that 1/8 floating around out front that I need to multiply by.
Okay, so wouldn't that equal 1? So that would...
No, because remember, this part, I need all of this part to get sucked back in. That 8, so look at it this way. How can you always check your antiderivative?
Take the derivative.
Take the derivative. So if I think the antiderivative is this, if I think it's 1, and I want to take the derivative, what will I get? I'll get e to the 4x squared times 8x. What did I start with?
4x squared.
I just started out with, all I had was an x. So this derivative is 8x, and this one was just an x. So I can't have, so really, if you think about it, I expected an 8x, but I only had an x. That means I only have 1/8 of what I expected to have. Instead of all 8 x's, I only have 1x. I only have 1/8 of them. That's another way to think of it. So the thing is, this is a complete derivative, right? It has all the pieces, including the constants. So that when I look at this piece altogether gives me this. Anything floating around out front just has to get multiplied through, because what do I know about multiplication by a constant? Carries through. So can I just stick in, so if I start with this original problem, can I stick an 8 in there because I feel like it? Right? You can't, wouldn't that be nice? I have $100 in my bank account. No, really, I have $800 in my bank account. That's fine. It's all good. Right? You can't just throw in an 8 because you feel like it. But if I put in an 8, I can also divide by an 8. Now have I changed the problem? I haven't, because 1/8 times 8 is 1. So I haven't changed the problem. But now this 8 I'm going to group this way. And this 1/8 I'm going to group this way. So I multiply by 1, but I put them in different places when I go to work the rest of the problem. So now this piece is the complete derivative, antiderivative. This piece is now the multiplication by the constant out front that carries through. Yes?
So does that go the same for like if you have a portion of the number? So instead of just
Yes.
like if you have 2 or 4?
Yes. So let's look at that. What if instead of this one, yes, that's an excellent. So yes, let's stay on this one and look at that. So what if I had this instead? So what if I had that? Is it a basic? Are you raising your hand or stretching?
Oh, it was kind of good. Try and answer it.
Oh, okay. Well, so yeah. So is this a basic? No. So what do I know that it is? It's a reverse chain rule because I have a composite function. The derivative of the inside is 8x. Do I have it? Yes and no. This part, the important part I have, I've got the variable because I can't mess with variables. I can multiply by numbers. You know, numbers carry through. I can multiply by weird, 8 over 8 is 1. I can mess with numbers, but I can't, the variable's got to be there. So the important part's there. So I have a 2 and not an 8. So there are a couple ways to handle this. You could say, well, what do I need to multiply the 2 by to get to the 8? 4. So I could multiply by 4. Can I multiply by 4 because I feel like it? No. So if I multiply by 4, I also have to divide by 4. Now have I changed the problem? No. I changed the problem, but not fundamentally because I've multiplied by 1. I haven't created some weird new problem. I've just rewritten it in a creative way. And we do this all the time when we're doing fractions, right? When we go to get a common denominator and we multiply by x over x, like we did for the average cost, that's a creative value of 1, right? We do that all the time. But now this piece that's inside the integral sign, this whole piece now that I have the 8 and the x, this whole piece is exactly the whole derivative. So now I've got the whole derivative. So I've got e to the 4x squared plus c. Multiplication out front carries through. Because I wanted 8 x's originally, and I only had 2 x's. So if I only had 2 x's, I only have a quarter as much as I need. So there's the quarter. There's another way to do this. Let me just throw in one more.
Wouldn't you have to 1/8 out in front as well?
No, because here I already had the 2. This is a slightly
I
different
think what
problem.
people are confused about is they don't understand that the stuff on the left side is getting sucked back into the top, and they're not understanding where that's
Ah,
going.
all right, so
But
let's-
I get that now.
Okay, so let's look at it this way. Let's look at it this way. So, if you're presented with a problem like this, maybe the problem is that it's split, and some's on the right and some's on the left. So when we normally write it, when we're doing chain rule, it looks like this to begin with. So if you want to, you can rewrite this one this way. I need an 8x, I don't have it. If I multiplied by 4 to get my 8x,
Oh,
Yeah.
negative now, because they were separated.
what's that?
They were separated on the first time that you went through it.
Yes.
The 2 and the x.
Yes, but what I'm saying, yes, so what I'm saying is that if you see a problem that's written this way, if you want to write it more so that it looks more like this format, you can do that, because you can multiply in any order you want. So you can pull that 2 to go with the x. Now, if I make the 2 into an 8x, I've multiplied by 4, so I need to multiply by 1/4 on the outside. Now, this whole piece looks exactly like what I expected to, so now it's the full derivative. Yeah, is that better to write it that way, or? So, again, part of this is a familiarity. As you get more comfortable with it, having the 2 over here and the x, or the 2x in the front, I mean, you're going to find it kind of in all different pieces. Because normally, remember, how do we normally write this when we go to write it in sort of conventional format? We write the constants first, the polynomials second, and then the exponentials. So you might encounter it written this way because this is the way we normally write it, but this is the way we think of the derivative. So just know that multiplication, where it's sitting right or left, doesn't matter. That doesn't change anything. All right, so let's look at, one more, do I have this somewhere? All right, I was going to use a phrase which is really probably horrible these days. I was going to say let's beat a dead horse, but does anybody know that phrase? It sounds terrible when you say it, doesn't it? It sounds terrible. But let's just belabor the point. Let's go one more. So let's do this one. So let's say you have 3x e to the 4x squared. Ooh, yeah, this one's not going to multiply nicely like the other ones did by 8 or by 4. So let's look at another way to handle this. We still know we're looking for 8x. I really do I would love to see this on every problem, on every assignment and test, because that clearly tells me that you know what you're looking for, and that's the step that will help you. Yes?
I mean, why can't we just, I don't understand why it's any different than the other one.
It's not, except that I can't just multiply by 4, because I'm going to have fractions.
Yeah.
Right? Yes, hang tight, yes, we're going to have fractions, but so it makes it a little bit less.
Like 2 and a third. Like,
Yeah, no, we're not going there. So, yeah, we're not going to do that though. Okay, we always have, remember, all your fractions, we never anymore write them in the form they told you to write them in elementary school. 2 and a third, we never write that anymore. It's got to be 8, or that would be what, 7/3. All right, so let's look at how we do this. We need an 8x and we don't have that. So let's do 2 things. Let's rewrite it in the order we like. Right, we like the x on the backside because that makes us, that kind of helps us see that this is the outside and this is the inside. So where should we put that 3? I vote for putting the 3 out front. Right, you can multiply in any order. I'm just going to pull that 3. That doesn't, right, multiplication carries through, so it can carry back. So I'm just going to put it there. What number would I like to have here? 8. Can I multiply by 8 because I feel like it? No. So I need to multiply by 1/8 out front. Now here is going to be your constant when you're done.
oh.
This piece is exactly the full derivative. Good to go, e to the 4x squared plus c. Here is what's left. What is 1/8 times 3? How do I normally write that? 3/8. Okay. I recommend that, this is actually my recommended method. Anytime you have a number that's not what you want, I think you're better off to pull it out front, do what you know you need to do, multiply by the fraction to undo it, and now all your constants out front clean up very nicely. There's no confusion. So this is the method I recommend if you have any number here that is not exactly what you want. All right, let me show you, while we're here. Okay. Let's do one more example of how to do this one. So I'm gonna erase this, but leave the problem. So if you want to rewrite the problem, you can. There is a thing called U substitution. And for some problems, it's required. There is no other way to do the problem except U substitution. We're not going to cover those problems in this class. So what I'm going to show you, you may use or not use as your preference. It is the same process as what we just did. It's just writing it out a little bit differently. So look at it. If you like it, great. If you don't, not a big deal. So here's the thing. Let me make this an 8 to begin with. I'm sorry. It'll make it a lot easier to explain. So I recognize this as a full derivative, right? Because it's got the whole 8x. But let me suggest let's think of another way to write this. What if it was confusing me? Having all those x's running around was too much for me to think through. I could take this inside, and I'm just gonna call it u. I'm gonna make a u substitution. Everywhere I have a 4x squared, I'm just gonna put a u. Okay, so that'll take care of this, but now I've got some x's running around, right? What am I going to do with that? I have to do more. In fact, I had a dx. So if I'm going to switch over to u's, I got to switch from dx's to du's. So let's look at this. Du equals, can I figure that out? Anyone remember what this is back from chapter 3? This is a differential. Remember, we could do a du dx. Du dx, the derivative of this with respect to x would be what? What's the derivative of that? We've just done it like 1,000 times, right? 8x. So then I could write du is equal to 8x dx. Good so far? So you'll see where we're going in this will help. Now I'm going to use this and this to replace in this integral. Okay. E to the 4x squared becomes e to the u. Now I need all the du pieces. I need an 8, an x, and a dx. 8x dx. So these pieces here combine to be du. Is that a basic problem? What's the antiderivative of e to the u? E to the u. E to the u. Love that, right? E to the u plus c. Did I start in u's? No, I started in x's, so now I got to go back. But everywhere I had a u, I just put a 4x squared. It is more work. I agree. I don't use this method myself. It feels like more work. With that?
It makes so much more sense.
Yes.
See, there you go. Some people are like, no. Some people are like, yes. So let's do one of the other ones we just did, this method as well. Let's do this one.
You just have the leftover math after you substitute those parts of it.
Right. So let's try this one. Okay. So I really truly don't care which way you do. It really totally personal preference on this. They're both correct. So let's look at this one. Is it a basic? No. I do see composite. So as soon as I see composite, I say, okay, I'm going to let the inside equal u. Because that's going to, right then I get e to the u. That's simple. That's a basic. So the whole point of u substitution is to turn a composite into a basic. Okay, so, and then the piece is, if you can get, you save yourself time if you can go directly du equals 8x dx. That's the differential form. If you can't go straight there, do this piece first, du dx, multiply both sides by dx. You'll get to the same place. Okay, so now we need to start rewriting, but here's where it gets a little harder. So e to the 4x squared becomes e to the u. That's easy. Now what do I need? I need an 8, an x, and a dx. I got the dx. I got the x. Do I have the 8? No. So what I'm going to suggest is we do the same thing we did before. Pull that 3 out front. Okay, we're just going to pull. In fact, if you wanted to, even in the beginning, or in the front, you could just literally move it out front. I don't have the 8, so if I put the 8 in, I would have to divide by 8. So I still have this 1/8 here, right? But now I still have, now I have the whole pieces that I need. So I think use substitution is easy when everything works nice. When everything doesn't work nice, you end up doing a lot of the same stuff you did before. So then what do we have at the end? We have the derivative, antiderivative of e to the u is e to the u, 3/8 in the front. Did we start in u? No, you don't start in u, you can't finish in u, so 3/8, put back in what u is, 4 squared, x squared. Same answer. So I don't care which, how many people prefer u substitution? And how many people don't? And that's fine, I don't care. We'll run them both ways so that you can see them both ways. And then we'll go from there. So let's do I say we have dealt with e to the 4x squared perhaps enough for today. So let's move on to another problem. Let's look at this one. Yes. You know what I'm going to do? I'm going to